Hello, and in this statistics video I'm going to explain the logic behind and demonstrate how to perform in our simple effects analyses as a way to follow up a significant interaction in a factorially independent ANOVA. Now, this is a natural follow-on to my last video where we discussed factorial independent ANOVA, what it is and how to conduct it in R. If you remember from that video, factorial independent ANOVA is where we have two independent variables or more than two independent variables. We want to look at the effects of them on some continuous dependent variable. Now, we saw in that video that gives us two types of effects. It gives us the main effect of one factor on a dependent variable, so that factor on its own, completely forgetting about the other factor, but it also gives us the interaction between the two variables to tell us is the effect of one factor somehow influenced or dependent on the level you're at of the other factor. So that's what an interaction is telling us. But remember I said when we get a significant interaction, we need to do follow-up analyses to understand the nature of that interaction and where that dependency is coming from. So I think to make this a bit more concrete, we should just have a look at our example. So I've got the data that we used in the previous video open in our. One thing I should say before we begin is that the concepts we're going to be discussing here are making use of pretty much the same concepts as I talked about in the planned contrast video. If you've seen that, I'm not going to be going into detail about what the similarity is, but if you've seen that video, hopefully you might see some connection between what's going on here and what we saw in that video. So without further ado, let's take a look at our example. So the fictitious study that we ran we're looking at people's levels of positive affect, and we hypothesized that giving someone a happy message would make them happy and then giving them a dull message, but that this effect would be largest when the relevance was high. So we were hypothesizing an interaction, and indeed if we look at the analysis we ran last time, the message times relevance interaction was significant. So I sent out a video. One way we followed it up in that video was just to look back at the means, and we saw that indeed the effect of message, or the difference between the two messages, seems to be a lot lower for the low relevance condition than it is for the high relevance condition. So obviously looking at effect sizes is always important. Significant tests don't tell you everything, but it would be nice to have some significant tests to tell us is there only an effect of the type of message when it's high relevance, or is there an effect at both? So that's what simple effects analysis allows us to do. The first thing we need to do is, if we look at our data, we have a 2x2 design. It's 2x2 because there's two independent variables and each level has two groups. Now, for R to perform simple effects analysis, these two variables need to be combined into one variable that separately define each of our groups. So if you think about the 5 people that have a happy message and low relevance on one group, the people that have dull message and low relevance on one group, the people that have happy message and high relevance on one group, and the last group are dull message and high relevance. So we need a variable that captures each of those groups, but not split across two variables. We need a variable that captures it in one variable. So to do that, with this data frame object is called affect.data, where I've got the data stored. So I'm going to say affect.data, And then to add a separate column to our dataset, we use this $sign here. So I'm just going to call the column combined, because it's the combined groups of our two factors. So combined. And what do we want this to be equal to? Well, we want it to reflect each of our separate four groups. So to do that, we can use the generate levels function. So GL, and this is for creating groupings. So if we look down here, the GL function is going to take several parameters. The first two are the ones we need to worry about. So the first one is n. Now this is a little confusing, because if n usually means number of entities or number of participants that we're comparing. So there's 5 participants in each of our separate groups, so my instinct would be to go 5, but this is how many separate levels or how many separate groups do you want to generate? Well, as we've already discussed, there's 4, so we're going to say 4, and then the next number k is how many times do you want me to replicate or assign each group? Well, each group has 5 people in it, so we want to do 5 times. With that done, we can look back at our affect.data frame just to see what it's done, and we do indeed have a separate group capturing all our combinations, but it captures them as part of one variable, so we're doing well. Just for quickness, we're going to turn this into a factor so we can have labels on it. So to do that, I'm just going to say we want you to basically overwrite what's already there, overwrite the numbers. So I'm going to say affect.data combined equals factor, and the first parameter it's going to take is what information do you want to use to compute the factor. Well, we're going to say we want to use the numbers that are already there, so I'm just going to copy our reference to the combined factor, because that's where the relevant numbers are stored. The next thing we need to specify is what are the numbers for the groups that this factor can contain. Well, as we already discussed, our analysis has 4 different groups, and there are 4 separate numbers here, so I'm just going to say factor levels are different groups that I want you to label in any of the between 1 and 4. And we now need to specify the labels in the order that they appear in the data. So we're going to say labels equals C, and you need to do these in order. So our first group is going to represent the people who have a happy message in high relevance, so I'm going to call that a HH. The first group is people who have a happy message and low relevance. If we look up here, I got that wrong, sorry. The next is people with a dull message and low relevance, so I'm going to call that DL. The next is people with a happy message and high relevance. And the last is people with dull message and high relevance. So it's really important when you naming these factor levels that you know what order your data are stored in. So with that done, we can take another look at our data frame, and now we have each of our groups defined separately. So we're doing well. Now that was all preparatory stuff to allow us to actually do the analysis. Now we're going to need to do something called assigning weights, and this is where, if you watch the plan contrast video, this is going to help you. Basically, we need to tell R numerically what we want to be included or compared in a particular analysis. Because remember, as part of this ANOVA, we want to do two separate analyses. One comparing happy and dull messages for people that have low relevance, and another one comparing happy and dull messages for people that have high relevance, to see if relevance makes a difference to the effect of the message. So the way we're gonna do that is to say, we first need to define our comparison, so our separate comparison. So I'm just gonna say C1, and it's helpful to think about what you want before you do this. So I'm gonna do this is gonna be the test for low relevance. So I'm gonna say I want to compare the two groups with low relevance, but I want to leave out the groups with high relevance because they're going to be in a separate comparison. So again, the order is important here because our two low relevance conditions become first. They're the two that we're going to define first, because these numbers or coefficients or weights that we're going to assign the computer is going to assign them according to the order that the groups are in. So few simple rules that we can apply when we're doing this. Any group with a coefficient of 0 doesn't get included in the analysis, and we'll see in a minute why that's important in this context. But any group that you want to compare should have equal and opposite numbers on either side. So for a simple effects analysis, we can just always use +1 and -1. So if I want to do for the low relevance, I want to compare the happy and dull message within the low relevance condition. Then I want to get my two groups that I know are low relevance, give one a positive sign and one a negative sign, because we know the way it decides which things to compare is based on what the sign is. So because we want to compare both our relevance conditions, I'm gonna give the first low relevance condition, the happy people, a coefficient of 1, and I'm gonna give the second coefficient of -1. Now, even though this is the comparison making for the low relevance condition, so the high relevance don't matter, if we don't specify something, R is going to get confused. So for each of our high relevance groups, we need to say zero, zero. Now, for the second comparison, it's going to be the opposite way around, because we want to leave out the low relevance conditions and just compare the high relevance. So we're going to say C2 equals zero, zero, because remember that the first two are the low relevance and we've already dealt with them. So but the third one's a higher relevance, so want to give that a coefficient of 1, and the dull people are going to get coefficient of -1. Okay, so we've defined our specific comparisons or our specific hypotheses that we want to test individually. Now, for us to understand this, it needs to be in what's called a matrix. That's basically just a table of numbers. So without any text, without being in separate comparisons like they are now, it won't sit in a table of numbers. So to do that, we're just going to say our comparisons, or comps as I'm going to abbreviate it, are going to be equal to the C bind. So that means bind each of these individual vectors that I'm going to give you into a matrix, and a vector is just a line of numbers. So bind two lines, C1 and C2. If we run comps, we can have a look at what that means. So we have one row has our coefficient for comparison 1 for low relevance. So we see that the two first group sorts included in the comparison, and then we have C2, which has our comparisons for high relevance. So we know that they're right. To apply those to our ANOVA, we can basically run the same ANOVA as we did before, but we want to tell it these are the specific contrasts or the specific comparisons we want you to do. So in order to do that, we're just going to say, before we run our ANOVA model, we're going to say contrasts, and it's going to ask us which variable do we want to get groupings for our contrast for. Remember, this is why we had to do combined, because you can't specify more than one variable. So we want to say comparisons for our affect dot data combine factor the coefficients or the information for what you want to do for those comparisons is in the comps matrix that C bind function just created for us. So we're going to say comps, and I messed up. So, sorry, the value should be outside of the brackets. Inside the brackets, we're just defining what factor this applies to. So we're saying it applies to our this data frame here, but we want to apply it to the combined variable, and that's applied. So we can now run our ANOVA model, and it'll give us those specific comparisons. So we're going to follow a very similar procedure to what we did in the main factorial ANOVA video. So check that out if you don't understand any of this. But we're just going to create a model object, and we're going to say we want the model to be an AOV object, an ANOVA object, and we're predicting positive affect. That's our dependent variable. And in this case, we want it to be predicted from combined, because that's the variable that we attached our specific hypotheses to, and that formula applies to the data for that formula is in the affect dot data object. If we submit that, it runs fine, but that's not going to give us the information that we want. If we run that, it's going to give us some output, but that's just testing the effect overall. That's not giving us that's testing essentially the same thing as the original ANOVA. It's a one way ANOVA on all the separate groups. It's not testing what I want it to test. So it has actually tested it. It's not showing us it. So we need to modify this summary function slightly and say we still want a summary of the model we just created, but we want to split that summary slightly. So split, and it's going to say, well, how do I want it split? We want it split according to a list. And what I want it to list it according to is the different tests we've asked you to do on this combined factor. So we're going to say combined. And it's going to say, well, there are a number of things in the combined object, but I don't know how to display them. So we're going to say, we don't need to display those in a list. And we're then going to assign names to each of our comparisons. This just makes it easier to interpret and doesn't affect the analysis at all. But we need to look at the order of comparisons here and look at what they're comparing. So our first comparison was comparing both the low relevance groups, and our second was comparing both the high relevance groups. So I'm going to say low relevance equals 1, and the second one is high relevance. Equals 2. If you run that, we get our separate output. It's come out slightly squiffy because of the size of this what the significance indicators are slightly different line. But if we run it again, now that the window's a bit wider, we get a more easy to understand output, and this basically tells us that what we expected for the low relevance condition, whether you've got a happy or a sad message, doesn't make a significant difference to your level of positive affect. But in the high relevance condition, there was a significant difference. So in terms of interpreting our interaction, these simple effects allow us to say that, or allow us to be confident that the effect of the message only matters in the high relevance condition, or that a message has to be highly relevant for it to have an effect. So that was a simple introduction to how to do simple effect analysis in R. If you want more kind of information on simple effect analysis, and there are some really important caveats and problems in this technique that if you're going to use it, you need to understand. So I would highly recommend watching my other video on simple effect analysis, which I'll link in the description, to get a bit of a deeper understanding of mathematically what the simple effects analysis is actually doing. So with that said, thank you for watching this video. Hope you learned something and hope you enjoyed it. Subscribe if you liked it. Thanks for watching.